your host for tonight. And tonight we are going to learn how astronomers map the universe and what those maps can reveal. You see, in a broad sense, astronomy is all about understanding our place in the universe, our place in space, and our place in time. And it's only recently that we've really begun to understand where we actually are. In 1924, Edwin Hubble showed that Andromeda is a galaxy in its own right, and therefore that the universe is much larger than the Milky Way alone. 5 years later, he proved that the universe is expanding, and therefore that it had an origin in time. We now know that that origin was 13.8 billion years ago. But how did we get from that hot, dense, primordial soup of the Big Bang to the astounding complexity that we see around us today? To understand how the universe has evolved, we have to map that complexity. Tonight, Dr. Daniel Eisenstein will tell us about an ambitious project known as the Sloan Digital Sky Survey. It has created the largest 3D map of the universe ever made. With that map, we are learning how dark matter and dark energy have influenced the past and will guide the future of the cosmos. And, as with any map, it begins with a little dot saying, "You are here." Please welcome Director of the Sloan Digital Sky Survey 3, Daniel Eisenstein.
Well, I want to thank everybody for coming out tonight. It's really great to see such an enthusiastic crowd. And I'm going to be telling you about the work that we do in the Sloan Digital Sky Survey, or really a portion of the work that we do in the Sloan Digital Sky Survey, focusing on this phenomena of dark energy and trying to tell you some about how we try to map it, which involves this sort of fabulous events in the early universe involving large sound waves. So the outline of the talk, I'm going to give you an introduction to cosmology and dark energy, just giving you some basics. Then I'll introduce this idea of what's called the Baryon acoustic oscillations, these sound waves, that we use as a cosmic yardstick. And then I'll be telling you about the Sloan Digital Sky Survey. I'll try to go through a fair bit of detail on how we actually go about doing these observations. Then I'll tell you about our detections of this effect in the SDSS and tell you some about what we've learned about cosmology from that. So let's get started with the big pictures of cosmology. So the real, I think, primal question here is, what's the universe made of? So of course, the composition of the universe is a very basic question of physics. And as you may well know, this is something that's turned out to have very surprising answers. The first set of surprises were these ideas of dark matter. So when astronomers started measuring the motions of stars in our own galaxy or in other galaxies, or the motion of galaxies within clusters of galaxies, they found that these stars and galaxies were orbiting their center too quickly. And this indicated there must be more mass there that's holding these objects onto bound orbits. These days, we can actually see this quite directly with gravitational lensing. This is a cluster of galaxies. All the yellow objects are clusters of galaxies. And they're actually bending the light of a galaxy in the background. This is the same galaxy seen 4 times and being bent by the light of the galaxy. So from this, we can quite directly infer the amount of mass that must be in this cluster. And it's much larger than what the stars would provide. And the great surprise is that this extra matter, this dark matter, is not just more of us. It's not just more protons or electrons or whatnot. It actually has to have some exotic form, and we've been able to show that fairly directly. Well, having discovered dark matter in the context of galaxies and clusters of galaxies, astronomers set out to try to measure the total amount of dark matter in the universe. And to do that, we need to measure the motions on even larger scales. And the most extreme version of this is to try to measure the gravitational effect on the expansion of the universe itself. Christine just mentioned that we've known for almost 100 years that the universe is expanding. But if you have a universe that has more matter on it than you would then you'd expect that expansion would slow down over time because of the action of gravity, and that by measuring the amount of that deceleration, you would infer the amount of material. Well, I should pause to just give you a little bit of a sense of what it means to measure the expansion. So we're using Doppler shifts to measure how fast galaxies are moving away. And these Doppler shifts are really exactly like what you get when a police car is coming toward you or away from you. You hear the sound change. In our case, we're looking for the transition of particular atomic transitions in the spectra of galaxies and watching them shift in wavelength towards the red. This allows us to measure how fast the galaxies are moving away from us. And in a uniform expanding universe, then you expect that galaxies that are further away from us intrinsically are moving away faster. Basically, this is as if we all stood up and instead of sitting seat to seat next to each other, we all stood up and had to put one spare seat between us. In this room, that would be hard right now. But you would then see that if to get your neighbor to move away, your neighbor only has to move one seat. But somebody at the other side of the room has to effectively move 20 seats because we've got to stick in an extra seat between every pair of people. So this relationship between the velocity of a galaxy and the distance is called the Hubble relation. And for small distances, this gives us a way of measuring the relative distance to objects. Now, this recession velocity is also known as a redshift. And it's written as the letter Z. And so I will very often say the word redshift in this talk. And what I mean is this recessional velocity. And the word redshift comes into our lingo so much because redshift is when you measure an object that's moving away from us very quickly, it's very far from us. This means that the light has taken a very long time to get to us. And that means that light was emitted very early in the universe or earlier in the universe. So the measurement of redshift is also a measurement of the time that you're viewing that object at. When you observe a galaxy at higher redshift, you're observing a portion of the universe that is younger. And that's a very important thing. All right, well, let's try to connect this idea to how we're actually trying to weigh the universe. So here's a very simple plot of the size of the universe versus time. And we're here at the present day and at the present size. And if the universe were just expanding ballistically, if there was no forces on anything, things would just move inertially, and you'd have a linear relationship between the size and the time. And you would look back and you say, oh, the Big Bang is 14 billion years ago. But if you think that the universe is decelerating because of matter, then in fact it should be expanding quicker at the beginning, and then it should start to decelerate. And that means that the Big Bang, the time of zero size, is less time in the past. So that would say that objects at a given redshift should actually appear to be closer because they've traveled less, the light's traveled less distance to get to us. That means the objects would be a little bit brighter. So you would expect that by measuring objects at a given redshift, if you measure them to be a little bit, the brighter you measure them to be, the more deceleration there has been, and therefore the more mass there is in the universe. And the great discovery in 1998 from two teams studying high redshift supernovae was that the supernovae actually appeared to be too faint. They were not too bright, they were too faint. And they interpreted this as the idea that the universe is not decelerating but accelerating. This is a completely bizarre idea because gravity does not, gravity wants to pull on things. And yet somehow on the largest scales our universe appears to be getting pushed apart. So we label this as dark energy. So it's some unknown thing filling space. I actually usually joke that dark energy actually overstates our knowledge by a factor of 2 because all we really know is that it's dark. We don't actually know it's energy. But if you believe that it's energy, then it's actually outweighing all the rest of the matter in the universe by about a factor of 2. So here's just referring to this picture. If you observe the objects, if you think the universe is accelerating, then it decelerates initially, and then dark energy starts to turn on, and you actually get an acceleration at late times. And so you find that the accelerating universe, the photons have traveled farther, longer to get to us, they've traveled further, and therefore objects appear to be fainter. So we're left with this idea of a cosmic composition where we're here in the atoms pie, part of the pie, only 4% of the pie, and in fact, the stars are only about 0.5%. So most of the gas is not even in stars. Most of the atoms aren't in stars. But then we have dark matter, which is outweighing the atoms by 6 to 1. And we have dark energy, which is outweighing the matter by about a factor of 2. So what's the cause of this? Well, there have been many possible explanations advanced for dark energy, the most famous of which is the cosmological constant that Einstein actually introduced in an effort to try to make the universe basically stand still. He wanted to basically balance the universe, so the gravitational forces and this outward going force would exactly balance and the universe would stay static. We now know that's not the case, and that's why he labeled it his biggest blunder. But so might be the cosmological constant. It might be that we have some new force in the universe. We know about the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity. Maybe we've just discovered the fifth force, and that it's actually some repulsive force on the very largest scales. Or maybe we just don't understand one of the normal forces. Maybe we misunderstand gravity, and we like to think that gravity is always pulling on things, but maybe on the largest scales it actually pushes stuff around. Maybe this is some remnant of string theory, that string theory says things should behave in 10 dimensions. Maybe that, when it comes down to our scales, actually causes some bizarre acceleration on the largest scales. And this list could go on and on and on. And there are shelf feet of journal devoted to trying to explain dark energy. And I think, unfortunately, all of these explanations have some exotic or vexing aspect to them. And so, there's no one theory that's so aesthetically compelling that everybody agrees that that's probably the right explanation. Basically, if you ask the proponents of the theory, they all love their children, but to get them to love other people's children, not so much. So what can we do observationally? Well, the main thing we try to do is measure very accurate distances. So I said that the supernovae were measured to be too faint. That means they're too distant. And we're trying to measure extremely accurate distances. We want to do this to of order 1%. Now, this is very challenging because throughout the second half of the 20th century, astronomers were arguing about something called the Hubble constant, and they argued about whether it was 50 or 100 in some particular units. And so there's a factor of 2 disagreement in the distance scale of the universe. People actually were disagreeing on how far away the galaxies were by the factor of 2 level, and we're now doing this at 1%. So how do we do this? Well, we're doing it with something called the Baryon acoustic oscillations. So this, in brief, I will explain this in much more detail in the slides coming up, but in brief, sound waves that propagate in the first 400,000 years after the Big Bang, so very early on, these sound waves create a very distinctive feature in the clustering of galaxies. And that feature is that pairs of galaxies, if I have 2 galaxies, they are slightly more likely to be separated by 500 million light years than they are by 400 or 600 million light years. So there's a characteristic scale of the clustering of pairs of galaxies that's imprinted in the early universe. And when we get to see this scale, then we get to infer distances. Because if I tell you that I'm 6 feet tall, you just get to break out a protractor and measure what the angle is from my head to my feet as it appears to you, and then you can infer the distance from me to you. So just by telling you how tall I am and allowing you to measure angles, you can measure distance. So that's the idea. This is called a standard ruler, and that's how we use this. Okay, so let's start trying to explain these sound waves. Well, we're going to start with the cosmic microwave background. So the cosmic microwave background is the radiation, the relic heat left over from the Big Bang. And to call it heat might sound ambitious even for Bostonians, because this is only 3 degrees above absolute zero. So this is a relic heat left over 3 degrees above absolute zero. But it's incredibly useful, because this radiation has traveled to us basically unimpeded throughout the history of the universe from a time only 400,000 years after the Big Bang. And this is a picture of the microwave background. This is now a projection on the sky. And you can see the early universe was exceptionally boring. Very, very simple place, very, very homogeneous. Well, when you turn up the contrast, if you take that picture and you now try to focus in on tiny details, instead of looking at 3-degree black body differences, you're now looking at 3 millikelvin, so 3 part in 1,000 variations in this map. And now you start to see some behavior. You see that one part of the sky is a part in 1,000 hotter than the other part of the sky, than the other direction. This is actually caused because we are moving relative to the microwave background. So when you move, then the part that you're moving toward gets a little bit of a Doppler boost. It appears to be a little bit hotter. The part you're moving away from gets a Doppler recession and looks a little bit colder. So that's basically boring, again, because that's only about us. That's telling us how we are moving. It's not telling us anything about what the rest of the universe is doing. To see how the rest of the universe is doing, you have to turn up the contrast by another factor of 100. And this was the great discovery by the COBE satellite, that when you finally blow up the contrast by now a part in 100,000, so we're now looking at 30 microkelvin variations in a 3-degree background, then you actually do see ripples in this map. And these ripples are coming to us from the very early universe. This is a picture of the density fluctuations on a thin shell 400,000 years after the Big Bang, 13.7 billion years from us. So we're looking at a gigantic sphere, 13.7 billion years in radius, and you're looking at the density fluctuations along that sphere. Well, that was the map as we had it in 1992, and since then people have been working very hard to try to improve this, and a major step forward was the WMAP satellite. This was the picture now in 2003. And in this past couple years, we now have the new map from the satellite called Planck, which is improving the resolution more and more and more. So these fluctuations are tiny, only a part in 100,000, but they're incredibly important because the details of these little ripples are actually telling us about the composition of the very early universe and about a fair number of other things as well, but they're really exceptional for measuring composition. So let's try to understand that. Well, now we're going to get into this idea of the acoustic oscillation. So if I look at this map from the WMAP case, when you look at the temperature fluctuations, you see fluctuations on large angular scales. This region is a little hotter than that region, for example. And you see fluctuations on small angular scales. But if you take just a part of this map and you blow it up and you just look at it, your eye is drawn to a characteristic scale of the blobbiness. There is a scale in this map, a sort of typical size of the blobs. And that is not caused by the resolution of the telescope. That's actually caused by a very important physical process in the early universe. So the way that we analyze maps like this is by taking them and splitting them up into their wavelengths. So basically we're trying to split them up into the long wavelength modes, the medium wavelength modes, and the short wavelength modes, and plotting how much variation there is as a function of mode. So it's like taking a piece of music and trying to figure out how much of the volume is in low C, how much is in middle E, how much is in high G, and plotting that up. So this was the picture that came from the WMAP satellite of this big bump at 1 degree angular scale. So this was this characteristic scale. Your eye is picking out a 1 degree sort of dominant frequency in the map. And you also see harmonics after this. And if this picture looks too impressionistic, this is the picture from the Planck data, 1, 2, 3, 4, 5, 6, 7, and if you squint at the yellow points, the 8th and maybe even the 9th peak. So these are basically overtones of this fundamental scale in the early universe. You're seeing a harmonic, you're seeing a fundamental mode and then the harmonics of it. Much like if you have an organ pipe, you get the fundamental mode of the organ pipe, and then you can get overtones of that mode. So what's causing this? So these are actually caused by sound waves that propagate in the early universe. Now the key idea here is this idea of recombination. It happens at redshift of 1,000. So when the universe is 1,000 times smaller than it is today, 1 billion times denser, 1,000 times hotter. And this is 400,000 years after the Big Bang, this age I've been telling you about. Okay, why is this important? Well, it's important because prior to this time, the universe is sufficiently hot and dense that it's actually ionized. So all the atoms have had their electrons plucked off. So you have basically electrons and free nuclei floating around instead of neutral gas. This is very important because free electrons are extremely good at scattering photons. If you try to send a photon through such a medium, it immediately scatters around. If the atoms in this room were all of a sudden to become ionized into a plasma, aside from all the other horrible things that would happen to us, we would not be able to see each other. So the light would bounce around very quickly. Now the reason this is so important is if you now take a packet of this gas, this plasma, and you squeeze it down, the photons are trapped inside. And much like if you take a piston and try to compress a piston, it heats up the gas. It heats up the photons. And those photons are providing an enormous amount of radiation pressure. Photons, like light actually does push on things. And so as you take this gas and squeeze it, the photons are getting higher and higher pressure. And eventually, they don't like the compression. It's actually going to push back out, and it will overshoot and become too cold, and the rest of the universe then pushes back. So the whole thing will just sit there and oscillate. This is exactly the behavior of a sound wave. It's really exactly like the sound waves that are propagating in this room. The only difference is that in this room, this restoring pressure is the random motion of the molecules in the gas, whereas in the early universe, the pressure is dominated by the radiation pressure of the photons. But aside from that, they're just sound waves. So this is very important. This means that all perturbations that get set up in the early universe from inflation are just sitting there jiggling as sound waves. This process comes to a dramatic halt after recombination. At recombination, the universe has cooled enough that the electrons bind onto the nuclei, forming a neutral gas, just like in this room. Now photons can travel just fine, again, like this room. So now if you take a packet of this gas and you squeeze it, the photons leave, and the gas just settles in more and more and more because of gravity. Gravity is just going to take over, and it's going to pull it in and try to form galaxies and clusters. So you have this major transition in the early universe where it goes from being stabilized where all perturbations oscillate as sound waves, to a situation where perturbations in the gas try to run away and have runaway collapse because of gravity. So a very major change. So let's see why this matters for us. So let's imagine a toy case where we just imagine a smooth universe that happens to be overdense at a single location. And it's overdense in dark matter, it's overdense in gas, overdense in neutrinos, overdense in photons. And because it's overdense in photons, it's also overpressured. This is coming out of the first second after the Big Bang with inflation. You'll get a region that's overpressured. And the way that an overpressure tries to equilibrate is by driving a spherical sound wave outwards. This is really, if I have a balloon that's overpressured, and all of a sudden I pop the balloon, you'll hear it, but you'll hear it because a sound wave travels out from the balloon to you. So the wave travels out at the speed of sound, which at these early times is fantastically large, 57% of the speed of light. It's a relativistic sound wave traveling outwards. That's because the radiation pressure is really strong. And it will travel out until you get to this epoch of recombination. At that time, the universe becomes neutral. The photons separate from the gas. And that means that the sound speed in the gas drops enormously, and the wave stalls. So you have this wave going out in the gas. It goes out for a certain distance, and then at 400,000 years after the Big Bang, it halts. Well, at that point, the universe is expanding. So wherever that shell has halted, it will now be carried along with the expansion of the universe. And it expands out to a distance that today is 150 megaparsecs, or in more conventional units, 500 million light years. So we have this characteristic scale of 500 million light years. Why does this matter? Well, because we have the dark matter at the center. That will preferentially attract material and form galaxies. And we have this extra gas at a shell of 500 million light years, and that will preferentially collect material and form extra galaxies. And so you predict that pairs of galaxies, if you have one galaxy at the center, you will have a slightly increased chance of having another galaxy somewhere out on that shell 500 million light years away. So pairs of galaxies are slightly more likely to be separated by 500 million light years than they are by 400 or 600 million light years. Okay, well that's distinctive. And why do we, why is it so useful? It's useful because this distance of 500 million light years is very easy to compute. It's really just the sound speed and the amount of time it has to propagate. And it turns out that the CMB anisotropies allow us to measure all the properties that are needed to compute this. And so we can calculate this scale of 500 million light years very accurately. With the latest data, we know the scale to 0.3%. So this is very unusual in astronomy. In astronomy, in most cases, you don't know how big something is intrinsically. If you look at a galaxy, you don't know intrinsically how big it is or how luminous it is. But this is a particular property that the early universe gives us that we actually are able to calibrate its size to 0.3%. At that point, we can use it as a standard ruler, measuring its angular extent, not only in the microwave background data, although that's a beautiful measurement, but also in low redshift data of galaxy surveys. And that allows us to measure distance as a function of redshift, which was our key path to measuring dark energy. All right, so I explained a universe that was overdense at a single location initially. In fact, the universe is perturbed at all locations. All locations emit their spherical sound wave. And so you don't get to see bullseye patterns in the data. Instead, you're going to see some pattern, and overlaid on it in some complicated way is these 500 million light year echoes. But it turns out that we can measure that well. I'll explain how we do it in a minute. But the challenge is that you need very large maps of the universe. This is a subtle effect, only a 1% little extra hiccup at 500 million light years. 500 million light years is a big scale, even for us. And so we need to have very large maps to do it. OK, so now I'll start telling you about how we map the universe. So the primary way that we do this is by using galaxies. So we want to use galaxies as signposts, especially measure the three-dimensional location of galaxies, and from that infer the density of material across the universe. So you start by measuring two-dimensional maps. So you just take pictures of the sky, and you can find the galaxies. The problem is when you see those galaxies, you don't know which galaxies are very luminous galaxies far away and which galaxies are smaller, wimpier galaxies really close to you. So you need to be able to tell the difference. And the way that you tell the difference is with spectroscopy. The more distant galaxies are going to have larger Doppler velocities, larger redshifts. And so you can sort the galaxies as a function of distance by using their velocity. You don't know the scale on it. You don't know the scale on the distance, but you at least get to sort them. The largest maps use about 1 million galaxies. And this is a picture of it from the SDSS where we are here. And this is looking out in redshift. So this is, let's see, that's about 2 billion light years away. So 2 billion years. And you can see the large-scale structure. This is just sort of a swath across the sky. So you can see that the universe has a lot of clustering. And we're now looking for a subtle effect on top of that. This subject has a very long history at the Center for Astrophysics. The Center for Astrophysics was really involved with a lot of the earliest developments in this field, most famously the stick man and Great Wall discovered by Margaret Geller, John Huckra, and Valérie de Leperrier. And so it's really fun to be able to pursue this work here. But I'll be telling you about the SDSS. The SDSS is the world's largest galaxy redshift survey. We use a dedicated telescope, 2.5-meter telescope, in New Mexico. It's above Alamogordo if you've been in New Mexico. The project actually got started in 1990, so it's 25 years old this year. We started taking data in 1998, which means that our first data can actually now apply for driver's licenses. And it's still running. We're running through at least the end of this decade. It's the world's largest compilation of astronomical spectroscopy. It's about 4 million astronomical objects. It's been generously supported over the years by the Sloan Foundation, Department of Energy, National Science Foundation, and over 50 member institutions. We now have about 1,000 people in the collaboration. It's really been a wonderful collaboration to be a part of. There's lots of different interests. Scientists from all around the world come together to work on this project, trying to blend their skills together. And it's really set the culture of astronomy in many different ways. It's been really a wonderful experience to be involved with. OK, so this is the telescope that we have. Does somebody want to tell me an unusual aspect of the telescope? Square. It's square, yes. There's petals on the top, yes. And there's no dome. So normally you're used to seeing telescopes inside of a dome. We actually park this telescope in a building. The building rolls off and leaves the telescope out in the open air. So this telescope, it's a 2.5-meter telescope, not a particularly large telescope by research standards. But it is unusual because it has such a wide field of view. So for these sorts of wide field surveys, it actually is really one of the most powerful telescopes in the world. What you see here as the boxy structure is actually not connected to the telescope. It's actually a wind screen to keep the wind off the telescope. And when the telescope's inside this, and when the telescope moves, the wind screen automatically moves around to track. So the first thing that we did is we took images of the sky. So this telescope conducted really one of the largest imaging campaigns. When you look in Google Sky or Microsoft Worldwide Telescope at the most areas of the northern sky, the image that you're seeing is generally from SDSS. Here's an entirely not random picture that we took at the telescope. This is M51. Here's a globular cluster M13. Basically imaging the sky using digital techniques in 5 different band passes. Here's a nice interacting pair of galaxies, galaxy group. And we repeated this for, I think, a total of 8 years, 9 years actually, conducting a big survey of the sky. So this is a picture now of the North Galactic Cap. So the galaxy, the Milky Way, would be around the edge here, and this is looking out towards the galactic pole. And this picture is unusual because we've actually removed all the starlight. We've gone into the images and removed all the stars, and all you're seeing here is the integrated light from the galaxies. And in this, you can already start to see some large-scale structure. These sort of lumps and darker spots are not. That's not just chance. There actually are large-scale structures. But these are the structures that are nearby. And you can see how much harder it is to measure structure in this two-dimensional map compared to the three-dimensional map that I showed you earlier. We also work at the part of the southern sky that we can see from New Mexico. So you can tip over in certain times of the year and see part of the southern sky. And all told, we imaged about a third of the sky. And all this data has been released to the public as of 2010. It's really a phenomenal amount of data. So if you just take a little chunk of this and blow it up to some not randomly chosen region, and then blow it up again, and then blow it up again, and you can, I don't think from where you are, you can actually yet see the detail in the picture. All told, it's 1 trillion multicolor pixels. So it's a 1 trillion pixel map of the sky. But we then want to continue and try to map in 3 dimensions. I've shown you this picture before. We want to measure spectra. And spectroscopy is much more expensive because instead of just collecting the light from an object, we're now trying to collect the light and split it up into a rainbow and measure 1,000 independent colors of that rainbow. And so we need much more light in order to do that. And so we can only do it on certain subsets of the objects. Until about 1990, all of the spectroscopy was done one object at a time. You basically would sit there and do one object, one object, one object. Well, it takes a long time to get up to 4 million if you're doing one object at a time. And so what we do is something called fiber spectroscopy. So basically, these are optical fibers, and they plug into this plate, and the light will go into those fibers and then transmit it off to the telescope. So I brought a couple plates here that you can see. So this is a plate that would go at the focal plane of the telescope. So basically, the light would bounce off the primary mirror, bounce up to the secondary, and come down and come to focus at this location. If this plate were covered with photographic film, then when exposed to the sky, you would actually get an image of the sky here. It would not be the whole sky; it'd be a chunk of the sky, about 6 full moons across, so about 3 degrees across, and you get an image of the sky. We take that image and we are then interested in particular subsets of objects. There would be about 100. We would detect about 100,000 objects on a chunk of sky this big. And we only have resource to take spectra of 1,000 of them. So we select which 1,000 we want. And then at the locations where the light from those 1,000 objects is going to fall, we go and we drill a hole at that location. And we will plug an optical fiber in that. And that means when the light comes down there, it's going to get trapped into that fiber and run off to the telescope. So I'm going to pass this around. I have 2 I'll pass around. And I want to warn you, you cannot hurt it. I promise there's nothing you can do that will hurt this plate, but it can hurt the head of the person in front of you. It has these little flanges. It weighs more than you think, so do be careful with your neighbors. But don't worry about being careful with the plate. So let me just say a few words more about the plates. So the fibers themselves, I should be careful. I'm probably knocking my little microphone. The fibers themselves are only 120 microns thick, so they're about the thickness of a human hair. The holes that you see in this plate are considerably thicker than that, considerably bigger than that. That's because the fiber is actually held for safety in a little metal tube at the end to give somebody, something to hold on to that they can actually plug the fiber in. If you just tried to plug a little, your hair into it, a brittle hair into it, it would break, and the survey would be over very quickly. So we have to protect the fibers. The fibers are actually, they're in these orange tubes, but again, that's just for their protection. The holes themselves are drilled to about 10 micron precision. So it's actually, these plates look simple, but they're very precisely machined because we have to get the light in just the right spot. And when we I should also mention then that, so they're actually hand plugged. So this is obviously sped up. It takes about an hour to plug a plate. You might wonder how we know which fiber went into which hole. It's very clever. We actually run the fibers are all running off to a sort of a one-dimensional slit head. They're all kind of coming to one dimension. So we actually shine a laser we actually run a laser down illuminating one fiber at a time, and you watch each individual hole light up in sequence, and you record that with a video camera so you know which order the holes were plugged. You'll see little lines on the plate. The lines, all the lines, each region contains 20 fibers because the fibers can't stretch all the way across the plate. So if you were just plugging anywhere you wanted, you would inevitably end up with the last hole over here and the last fiber over here, and then you'd have to start over. So you actually grab 20 fibers at a time, plug 20 fibers, grab the next 20, plug 20 fibers. That keeps you organized as you move across the plate. So let me start this off. You'll also notice it's big and heavy. That's because it has to be really stiff. So the focal surface is only about a few hundred microns thick. So you really have to have the plate really in the right location. And if you tip the telescope over, if it was floppy or weak, it would, the gravity sag would cause problems. So you really have to hold them in the right spot. So they're plugged by our dedicated workers at Apache Point. In 1 month in 2011, we had a really clear month. We plugged 100,000 fibers. So. All right, well, when the plate's all done being plugged, it goes off to the back of the telescope. This is actually the camera. The camera comes off, the plate goes on, and it sticks into these two spectrographs here. This is probably more easily seen in this movie. So it's just trying to give you a feel for what we do at the observatory. So this is the telescope over here. One of the observers is going to load one of these cartridges. These plates actually sit in these cartridges. They weigh about 300 pounds. Trying to hold things, they're really, really stiff, so you can't move them around by hand. You have to have mechanical aid. This is the bottom of the telescope, so he's going to wheel the cartridge in, lower the last cartridge, back up, insert the next cartridge, take it back, and load this thing up. So there's the building rolling off. We're getting ready for the night's observer. This is on a mountain at 9,200 feet in New Mexico, looking out over White Sands National Monument. If you've ever been to White Sands, you were actually very close to the telescope. And basically, we're really on the west edge of the mountain range. So the hope is that when the prevailing winds come over, they're basically coming over this valley for 50 miles, nothing to stir up the air. And we hope that the first thing that air encounters after 50 miles over the valley is our telescope. So nothing else has been able to stir up the air. So this is now sort of time-lapsing over the night. I'll skip ahead. But basically, load up the plate, observe a given spot on the sky for about an hour. And when you're done, then they're done. The plate, we basically, we only use the plate for an hour. So we've now drilled about 7,000 of these plates over the years to keep the survey moving. Okay, so let's try to look at some of the data. So this is now, this is going to be a movie of sort of flying through a big chunk of this three-dimensional map. It's hard to show 3D maps. So this is now showing sort of a thin slice of the map, and I'm going to move that slice along. I'm picking the slice to be at a given distance from us, so as the movie progresses, this black swath will move out, and that's going to correspond to the thin slice moving out through the survey. This is a fixed angle on the sky. This is about 20% of the survey volume, about 20% of the area. So this is about 4% of the sky. So I'm showing you basically 4% of the sky and then just a slice going out from us. To make the map a little bit dynamic, I start the objects off. When they enter into the thin slice, I'll start them off faint and red and then brighten them up to black and then dim them out to faint and blue. So you'll see things move around. And as we go through, you'll see you'll basically be slicing through the large-scale walls and filaments and voids of the universe, so you can actually see the large-scale structure of the universe. The black circle here has a radius of 500 million light years, so that's our characteristic scale. As the movie plays, you'll see that gets smaller because you're moving further away. You're looking at a slice that's further away from us, so that scale will appear to be angularly smaller. You'll also see the large-scale structure. The voids and patterns will actually appear to get smaller. That's because they're further away from you. You are actually seeing them further away. So this is the nearby part of the survey. You can definitely see some of the walls and filaments popping in and out. So we're now about 3 billion light years away. about 4 billion light years away. Now we're getting to the thick part of the survey, where we have a lot more data out here. So this is kind of the peak of the survey density. And once we get to the edge, now the objects are getting to be faint enough that we don't get a very high sampling. So the survey will start to thin out here as we get out to the edge, about 7 billion light years away from us. Okay.
The density is a function of the sampling, not of what you're actually seeing.
The density. So there are many more galaxies. There are truly many more galaxies than we're able to measure. We're basically measuring some representative sample of them as we move out, and that's a varying number. Okay. Well, qualitatively, that's the map. That's the kind of thing that's the map we're measuring, and we now want to try to analyze it quantitatively to look for these sound waves. The way that we do this is with something called the galaxy correlation function. So it's a relatively simple idea. Pick a galaxy and sit on it, and now count the number of other galaxies in a ring around that point. Now repeat that as a function of the radius of the ring, and then repeat that, picking every other galaxy in the sample as the center point and sum over all of that. And when we're done, then back in 2005, we got this first detection at a distance of 100 H inverse megaparsecs, about 150 megaparsecs. We found this extra bump in the large-scale correlations of galaxies. And this was exciting because it gave us a 4% measurement of the distance, but it also gave us a very clear connection between this beautiful physics that we're seeing in the microwave background with all these acoustic features in the microwave background only 400,000 years after the Big Bang. We're now seeing the imprint of that 10 billion years later in the clustering of galaxies. So emboldened by that, we started SDSS-III, and one of the major goals for SDSS-III is to use the acoustic peak to study the evolution of dark energy. We operated SDSS-III starting in summer 2008 and ran it for 6 years until summer 2014. And the part of the survey that's relevant to this is called the Baryon Oscillation Spectroscopic Survey, BOSS. And the goal was to produce a world-leading detections of the BAO over a wide range of redshifts. So the best acoustic peak we have at this point is this one. So this bump at 500 million light year radius. And basically measuring this bump relative to the blue line, the location of the bump relative to the prediction from the blue line, is what gives us our measurement of distance. And this actually gives us a 1% measurement of the distance to redshift 0.57. It's the most precise extragalactic distance yet measured. Well, we do this now at a variety of redshifts. So we have our measurement at redshift 0.3, which is a 2% measurement. We have this one at 0.57. There's another one at redshift 2, which I'm not going to have time to tell you about. And we have also, of course, the measurement in the microwave background itself 14 billion years ago. So when we just plot this and plot distance versus redshift, we have our points here. There's other BAO measurements from a survey called Wiggles and a survey in Australia called 6DF. So we actually are now piecing together the distance versus redshift relation of the universe by looking at this characteristic acoustic scale fingerprint. We're just seeing the same fingerprint at different redshifts, and by measuring the change in angle, we're measuring the distance out to all these different redshifts. Well, now let's see what we can learn about cosmology from this. So I'll start by showing you the prediction for this curve from the microwave background data, assuming that the universe is flat and has and that the dark energy is a cosmological constant. I'll come back and explain those concepts in a minute. But so just making those assumptions, you get this prediction for the curve. So you can see it's an amazingly good match of the low redshift data to this prediction from the CMB. When we zoom in, if you divide by the center point of the CMB, then you get this thing, and you can see that we're basically agreeing. We're finding agreement at the 2% level of the predictions with our measurements. So that's really wonderful to see it. And in detail, the low redshift data is an excellent match to this model. But of course, we could test other models, and so let's explore some of those tests. Well, in general relativity, one of the major ideas is that space is curved, and gravity is basically because we perceive gravity because this space-time is curved. And in particular, the universe as a whole is curved, and you can have options. So the universe could be flat, like a sheet of paper, I mean, if it was a two-dimensional universe, it would be flat like a sheet of paper. We're, of course, a three-dimensional version. Or it could be curved like a sphere. We could basically be like an ant living on the surface of a sphere. That would have curvature. Or it could be crinkled like a saddle, or a potato chip. And you can define universes like that. This curvature matters because it means that important things about geometry, like the idea that the circumference of a circle is no longer 2 pi times the radius. This is a familiar idea. If you're sitting on the North Pole and you walk down to the equator, and then you walk around the equator, you will find that you only have to walk 4 times as far as you did from the North Pole, rather than 2 pi as far. So curvature does matter. It also has the effect that angles of triangles, the sum of the 3 angles of a triangle don't add up to 180 degrees anymore. Okay, well, it turns out that the acoustic peak gives really wonderful measurements of this. And so if we make a plot of the density of matter in our units, let's not worry about it, but they're units called omega matter, and the density of dark energy, then if those sum to unity along this line, then you would have a flat universe. And by just looking at, so if it summed to more than that, you'd have a spherical universe. Less than that would be this potato chip or saddle universe. So our data from the acoustic oscillations is really strongly driving us back to a flat universe. And when we add in the fact we see the same fingerprint in the microwave background, you get driven down to this little region here. So the data, just seeing the same acoustic scale at all these different redshifts, allows us to very dramatically see that dark energy is there and that the universe is very close to flat. But of course, we also want to understand about this dark energy. And up till now, I've been saying, oh, it's a cosmological constant. Well, of course, we'd like to study if it's a cosmological constant. The cosmological constant is saying that a given volume of space weighs some amount. And the amount that it weighs is invariant with time. If you come back later on, it's going to weigh the same amount. But maybe it changes. Of course, it's very reasonable to think that it would change. If I take the universe and it expands, if it expands by a factor of 2 so that the volume is 8 times larger, the cosmological constant is saying there's actually 8 times more stuff because the volume increased by a factor of 8. That's kind of weird. So we'd like to see if this is changing. And we typically parameterize this by W. So W is -1 is the cosmological constant. And values other than -1 mean that this density is changing in time. So let's return to this previous figure that I showed, where before I showed you the red region and our data. But now let's imagine altering these hypotheses. So we're going to now take the predictions of the CMB. But instead of saying that the universe is flat, we're going to say that the universe has a 1% curvature. And that moves the prediction down to this blue region. Not as good a fit to the data. Or we could say that, oh, no, we'll keep it as flat. But now we're not going to assume the cosmological constant. We're going to allow the dark energy to change in time. And in particular, let's pick a dark energy that has gotten a factor of 2 weaker since redshift of 1. And that would give us this gray swath here. Again, not as good a fit to the data. So the data is really forcing us back to the flat cosmological constant model. And this is a version of that same idea where I've now plotted the curvature. So here's flat. And the dark energy density evolution. Here's the cosmological constant. And the data is driving us back to this blue region. So this is very remarkable. We've taken what we thought was the simplest model, a flat cosmological constant model, and we've opened up 2 degrees of freedom, 2 new parameters in the model, allowing the spatial curvature to vary and allowing the dark energy to evolve in time. And the data is driving us back to the simple model. So it's very interesting evidence for that simple model. Okay, so we've really had a remarkable few decades in cosmology. And we now have, I think, a very concrete and simple and elegant theory for how the universe works, starting at an age of 1 second with the formation of helium and deuterium and the light elements, on through today on scales from galaxy scales up to the scale of the observable universe. And it's really a triumph that it's been able to be tested in so many different ways. We have lots and lots of cross-checks, lots of confirmations. And this theory is very important, not simply because it explains these cosmological observations, but because it gives a very robust base. It has a very specific prediction for the initial conditions of the universe, and that allows us to simulate forward and provides the basis for all of our studies of galaxy evolution and the evolution of cosmic structure. But along the way, we've discovered this very elegant theory has two new ingredients, dark matter and dark energy, and we don't know what they are. So this is really the opportunity for the next decade or for next decades to explore these topics, to try to figure out what dark matter and dark energy are. And it's going to be a very exciting decade because we have a lot of new facilities that are going to be improving our maps. I work on a project called DESI, which is going to be using the 4-meter telescope at Kitt Peak to do these surveys on even larger scales. There's a big project called the Large Synoptic Survey Telescope, which is going to be imaging the sky every 4 nights to build up a very deep map of the universe. There's a European satellite mission called Euclid, which is going to map the sky in great detail. And of course, once you have these maps, you want to actually be able to go and understand individual galaxies in that, and that's where the Giant Magellan Telescope that Jeff McClintock will tell you about next week comes in. So these facilities are just going to bring a very large reach on cosmology. We have the opportunity to improve these maps by a factor of order 100 over the coming decade, and just get to lots of interesting new phenomena in cosmology. So to conclude, I hope I've convinced you that acoustic oscillations are providing a very robust way to measure the cosmological distance scale, and with that, starting to probe the nature of dark energy. It's based on very simple physics from the early universe that leaves a very clean, albeit weak, signature in galaxy clustering. And this method has really matured over the last 10 years to being a very important tool in our study of the cosmic expansion history. Within SDSS, we've used the acoustic peak to measure distance to percent level accuracy, and we find really excellent agreement with a flat cosmology with the cosmological constant. And there's lots more to do because we really want to understand what dark matter and dark energy is, and so the next generation of astronomers have a lot of work to do. Here's my son making an early suggestion. So I'll invite you to learn more about our survey at www.sdss.org, and I'll be happy to take any questions. Thank you.
All right, time for questions and answers, and the gentleman in plaid had his hand up first.
How do the instruments you're using compare with the James Webb instrument that they're going to launch in the next few years?
Yeah, so James Webb Space Telescope is the successor to the Hubble Space Telescope, and it's a telescope that's optimized for infrared observations in space. It's a very narrow field telescope, so it really looks at pinpricks of the sky, but it looks enormously deeply and looks in the infrared. So we're doing wide field surveys primarily in the optical. So James Webb is extremely important for understanding the early galaxies, the formation of early galaxies. We'll be able to dissect really the evolution of galaxies across a wide range of cosmic history. But ultimately, it only covers tiny fractions of the sky, so it's not as good at mapping things. You want to map things, but once you find interesting things, you want to go and look at them in detail.
Yes, sir.
Electromagnetic energy requires no medium for its propagation. My understanding of acoustic energy is that a medium is required for it to be propagated. I'm probably missing something in your definition
Well, a medium
of acoustic.
is so these are waves that are propagating because of the motion of